Okay, so hopefully that diagram helped you just kind of summarize that main theorem here. Differentiability implies continuity. So how I just remember the visuals, I just remember the small circle is differentiable and the big circle is continuous. And I kind of just logically figure out those three statements based on the visualization of the small circle is differentiable and the big circle is continuous, and then draw a box around it to show that there's a world outside of continuity and differentiability also, to get all three of those statements, because for me it's hard to just memorize those statements, so that's how I get that visualization. For me it's just easier to remember which circle goes in which, and then from there figure out those three statements. Okay, so I want to now just do an example, so you'll get more practice with this in class, but it says use the graph to identify the x values where the function is not differentiable. All right, so you want to look at the x values here, and so remember that if the function's not continuous at that point, it's not differentiable there. So at x equals -3 and x equals 4, the function is not continuous. So it's not differentiable. At x equals 3 and 4. -3 and 4, I'm sorry. Okay. So now, there are more points, however, where I do fail to be differentiable. So here, the other ways I could fail is if there was a vertical tangent line, which, looking around at these points, there isn't a vertical tangent line to any of these points. If I drew tangent lines to these points, I would not get a vertical tangent line, so I do not have to worry about that. However, with -2 and 2, these do have corners or cusps. So here, I would say that the function is not differentiable at -2 and 2 because of the corners / cusps. So the function has a corner / cusp at x equals -2 and x equals 2. So f is not differentiable at x equals -2 and 2 as well. So the answer, final answer that you should have is -3, -2, 2, and 4 are all the x values where the function is not differentiable.